Hello, everybody. I hope you are doing well. As a student of mathematics, you have graphed a lot of functions in your entire life, I am certain. All right. Now you have learned a lot more stuff since the beginning of Calculus 1. And so now you are equipped with more tools with which to graph various types of functions. So in this section, which is section 4.6, we will be learning about limited infinity, asymptotes, and graph sketching in general. All right, let's get started. Okay, so when you sketch the graph of a function, by the way, the word sketching refers to sort of a roughly drawing the graph of a function. So yes, you can look at all the details and you can draw a very careful, accurate graph of a function. But at the same time, many times you do not need all the details. You just have to know what the overall graph looks like. So the idea of sketching is, let's just pick up some of the main characteristics of the graph and try to draw, a big picture of the graph. And that's what the idea is. In order to do this, I will first talk about limits at infinity. Basically, this is the question of what happens to f of x as x approaches positive infinity or negative infinity, because that's going to tell us a big picture of what's going to happen with the function. Asymptotes, all right, this is closely related to this limits at infinity and a few other things. And that's our beginning point, because if you remember, in fact, recall asymptotes, you have learned a few types of asymptotes, mainly three actually, depending on how they are oriented. You had vertical asymptotes, VA to abbreviate that, and then horizontal asymptotes. These are horizontal lines, HA, horizontal asymptotes. And then the last one, it goes by a couple of names depending on which textbook you use. Oblique asymptotes, OA, or sometimes these are called slant asymptotes. And basically, this is all asymptotes that are not vertical or horizontal. All right, so can you come up with each of these things? Like what would be a good idea or a good example of a function with a vertical asymptote? So if you want a vertical asymptote here, let's say, x is equal to 2, that's a vertical line. Can you come up with a function whose asymptote, or at least one vertical asymptote, is x equals 2? Yeah, the key is to come up with something that blows up to infinity as x approaches 2, right? Both from the right and the left. Maybe this will be a good one. Okay, so that is what, what 1 over x looks like. 1 over x is, this hyperbola. If you move it 2 units to the left, you have, 2 units to the right, you have this function. And you can see that, when x is equal to 2, the function is not defined. And that's typically what happens when you have a vertical asymptote. Now you can define, a particular point like this or something, but you don't have to. There is a vertical asymptote here, right? Vertical asymptote, in this case, is 2. By the way, there's also a horizontal asymptote, because as x approaches infinity, this gets closer and closer to 0. And as x approaches negative infinity, this gets closer and closer to 0. So this picture, this one particular graph, a rational function, illustrates both a vertical asymptote and the horizontal asymptote, right? How about an oblique asymptote? Can you come up with an equation that has an oblique asymptote? Maybe, do I have a dotted line here? Yeah, I think I can draw a dotted line. And so if you want, let's say this, y is equal to x. Looks like it, right? If you want this to be an oblique asymptote, then you could come up with something that gets closer and closer to that, right? So an example would be something like that goes like this, right? So this goes up to infinity, and this one gets closer and closer to the line, right? And an example of that is, well, if the function itself is getting closer and closer to y is equal to x, then it makes sense that f of x is x plus something that approaches 0. And how about something like this, okay? This happens to be a function that sort of looks like this. And you can also see here, you have a vertical asymptote. X is equal to 0, which is coming from this denominator. All right, so these are some of the examples of asymptotes. Again, asymptotes can be classified into three types, and those are vertical, horizontal, and oblique asymptotes. All of these discussions can be presented without ever defining what an asymptote is. And if I ask you to define the word asymptote, you probably will have a very difficult time. And I didn't realize this, but until much later in my life, did I really understand what an asymptote was, okay? And the reason is because this idea, the asymptote, is a very hard word to define, okay? So what do you say? A line L is an asymptote. This is, by the way, an unofficial definition, but it's pretty close to the official definition. A line L is an asymptote of F if what? The idea is, as you go farther and farther to the right or to the left or up and down or away from the origin in all kinds of directions, right? And it doesn't specify which direction you go to. You just have to go farther and farther away from the origin. That's a hard thing to describe mathematically, but we can try to do that. So one version of an unofficial definition would state something like this: a line is an asymptote if the distance from L to the graph of F approaches zero. So you want the approaches zero. You want the asymptote to get closer and closer to the graph of the function f, right? I mean, after all, that's what the asymptote is. It's a line that the graph gets closer and closer to. Approaches zero as what? As the points of L moves farther and farther away from the origin. And you do not specify farther away from the origin. You do not specify the direction so that it can go vertically or horizontally or in an oblique fashion. The point is, as you go farther and farther away and without bound, you just have to let this go infinitely far. And as you do so, the graph is such that the distance from the graph to the line L should get closer and closer. Now, many people make a mistake by saying or by adding to this statement that the asymptote can never touch the line. All right, and that is also a very commonly made mistake. It is perfectly okay for an asymptote to touch or cross or coincide with the graph of a function. All right, and again, this is something that is taught erroneously in many schools, but you will see that some of the asymptotes we will see across the graph at 1 or 2 or infinitely many points. Okay, all right, so with that in mind, let's go ahead and look at some of the examples. All right, so if you see y is equal to 1 over x, this is a reciprocal function, and you know what this graph looks like. It is known as a hyperbola, and as x approaches infinity, what's going to happen? Well, f of x, y approaches 0, right? This approaches 0. And that is what we call, or we will be calling in a few minutes, the limit at infinity. Okay, limit at infinity. So here you see the horizontal asymptote y is equal to 0 to the right and to the left. All right, so you can see that. And here is another example, e to the x. Okay, so e to the x is kind of strange function. It goes like this. And the first one, this was an odd function. The first one was. This is not an odd function. And you know e to the x grows exponentially. I mean, like literally exponentially, because it is an exponential function. But as x approaches negative infinity, it gets closer and closer to 0. So you do have an horizontal asymptote, y is equal to 0. Okay, so both of these horizontal asymptotes, you can see that this is a line that represents the limit as the function approaches infinity, right? So the question here is, what happens to f of x as x approaches infinity and or as x approaches negative infinity. And so here is the first definition, the official definition that we are going to learn in this section besides the asymptote, which was, we tried our best to represent what the asymptote was. All right, so number one, we say the limit of f of x as x approaches infinity is equal to L if f of x approaches L as x approaches infinity. Now that's like saying, well, of course that's exactly what this means. I mean, that's what it says, right? And that's true. Now that's an informal definition. Remember, we had an informal and a formal definition of a limit. And so this is the informal version. Basically, all it says is f of x gets closer and closer to L, where the difference between f and L approaches 0 as x approaches infinity. Now, of course, there is a more carefully worded definition. I don't know if you actually want to hear this or listen to this or watch this, okay? But the technical definition goes like this. You remember the formal technical definition, the mathematical definition of a limit that has epsilon and delta? Well, this is, it's not surprising that you will see at least one of those Greek letters. This one says for every epsilon greater than 0, there exists. Now there's no delta here because you want x to go to infinity. There exists a capital M or some large number M such that whenever x is greater than M, then f of L and M gets less or is less than, guaranteed to be less than epsilon. So again, epsilon could be a very, very small number, but regardless of how small the epsilon given is, can you find M, maybe 10,000, 100,000, maybe a million, so that when x is over that number, then f of x is very, very close to L. In fact, it's so close that it's less than the given delta. And if you can do that, if you can provide such an M for every delta, we say the limit is L as x approaches infinity. Now, the same thing, I'm not going to rewrite the formal definition for the limit as x approaches negative infinity, infinity. But this one basically says this one that says f of x approaches L as x approaches negative infinity. You just let this keep going to the end, to the left end of the graph, and if f of x gets closer and closer to L, then you say it's the limit at infinity. So these are called limits at infinity and at negative infinity. Makes sense, right? Even though x never actually gets to or reaches the infinity or negative infinity, because clearly these are not numbers, right? Okay, so the fact is, you probably guessed it, y is equal to L is a horizontal asymptote of L, of the function f, if the limit is L as x approaches infinity or as x approaches negative infinity. So either one of these cases, you will have an horizontal asymptote. Okay, I'm going to give you several examples of this. We saw something similar to this, 1 over x. 1 over x squared, that's similar to 1 over x, except it's an even function. So in both directions, you notice here, this f of x is never a negative number, never even 0. And so you can see the horizontal asymptote here is 0 as x approaches infinity and as x approaches negative infinity. Normally, I mean, I should be writing this as two different limits, but x approaching positive and negative infinity, you can see the same thing here. All right. What about tangent or inverse tangent? I told you this is a pretty important function. In fact, this is one in which I take delight. This is such a wonderful function for a few reasons, but this is the inverse tangent is defined as you restrict the domain of the tangent function from negative pi over 2 to pi over 2. And then, of course, you have to switch the x and y to find the inverse tangent. You know, the tangent function restricted to that domain goes like this. So the inverse tangent is going to go like this and makes a curve and goes that way. Okay, so how many horizontal asymptotes are there? Well, there are 2. Okay, and that's because the limit of the inverse tangent of x as x approaches infinity is pi over 2. And in fact, it's always going to be less than pi over 2, but it approaches that value. The inverse tangent of x, well, the limit of the inverse tangent function as x approaches negative infinity is negative pi over 2. So we have 2 horizontal asymptotes, okay, for the inverse tangent functions, the inverse tangent function. All right, how about something strange like this, sine of x over x? Okay, so this requires some thinking. What thinking are we talking about? All right, notice here, sine of x over x is always less than or equal to 1 over x, right? I mean, simply because sine of x can never be greater than 1. It's also never going to be less than negative 1. So it's between those. Now, 1 over x, let's go ahead and draw this with a dotted line. 1 over x looks like this, okay? Negative 1 over x is similar. Basically, it's, you know, well, it's supposed to be all symmetric here. So it looks like this, okay? All right, and sine of x over x is sandwiched between them. And by the way, you also recall that the limit of the sine of x over x, I mean, using the sandwich theorem, approaches 0 is equal to 1, right? But sine of x over x is not defined at x is equal to 0. So there's an empty hole here, but the hole is at this point 1. Okay, so this circle is located at the point 0, 1, but there is no point on the graph for this because of the 0 denominator. Okay, so what's going on here? Well, the sine of x over x is basically kind of go like this, and it's always going to be sandwiched between these 2 numbers, right? And by the way, sine of negative x is negative sine of x. Negative x is, you know, negative x. So if you switch x with negative x, you have sine of negative x over negative x, and that's negative sine of x over negative x. And so that is still the same as f of x, which means it's an even function. It doesn't matter if you have positive x or negative x. And it's restricted, sandwiched between these 2 values, 2 functions, this and this. So it'll never go outside of the hyperbolas that you have, the 2 hyperbolas, the 2 sets of hyperbolas. Okay, so the point is, this graph is, you know, it's hard to find. I mean, it's hard to draw, okay? But you know that it's going to be oscillating up and down, bounded by these, you know, lower bound function and upper bound function. And so the answer, the sketching will look like this. You have infinitely many local maxima and infinitely many local minima. The horizontal asymptote, there is a horizontal asymptote. Y is equal to 0. Okay. Notice here, fx crosses. So, you know, if somebody says, if one of your friends or maybe a former teacher, I hope not, says, hey, look, you know, the asymptotes cannot ever touch the graph of the function. This would be a great example to show And you can say not only can the graph touch its asymptote, it can do so infinitely many times. Infinitely many times. I guess I should say the horizontal asymptote infinitely many times. And it is quite possible, right? And this does satisfy the definition of an asymptote. And so the line y is equal to 0, otherwise known as the x-axis, is the only horizontal asymptote for this function sine x over x. Okay. So that's the limit at infinity. Now, the book talks about casually, informally about this idea of the infinite limits at plus or minus infinity. So what do we mean by that? Well, if the limit is infinite, that means it just goes, to infinity as x approaches infinity or something. And basically, this is all, the end behaviors. Maybe I should say that this is very, very closely related to what we know as end behaviors. You could say these do describe the end behavior. So the idea is this: if you have a function, close to the origin, lots of things could happen. You could have a bunch of ups and downs, whatever. But eventually, okay, after the mess, sort of, in the middle of the universe happens, eventually the function may just keep going this way and this way. This happens, for instance, x to the 4th or x to the 14th or whatever, x to x to an even numbered exponent. Eventually, the polynomials will be like this, okay? So here we can say the limit of fx as x approaches infinity is infinite. Now, is this a limit? Well, for a limit to exist, this number should be finite. So as soon as you write this, you are almost admitting that there is no limit, and therefore, as you can see, there's no horizontal asymptote related to this. But some people say the limit at infinity is infinite, to indicate that the graph basically continues to go up as x approaches infinity. If you say the limit of fx as x approaches negative infinity is infinity, again, you are describing a behavior that you see right here. Okay, and if you have some other things where all kinds of things are happening here, but eventually the function goes like this, you can say the limit as x approaches infinity is infinite. Again, this is this right upward arrow. But here, the limit of fx as x approaches negative infinity is negative infinite. Okay, I mean, you can say that the limit is not finite. It's negative infinity. That just means it keeps going down, down, down. And it doesn't, ever approaches any horizontal line. It crosses every horizontal line and continues to go down. That's what this means. Okay, so I will not write careful definitions of these, but you can see that in the book if you like. I don't think we'll be using those carefully phrased mathematical definitions of infinite limits at positive or negative infinity. But I can give you examples. Here you can see this in like x to the 6th power or the 8th power or any, x to any even numbered power. And here, for x to an odd numbered power. And I think you learn these things as end behaviors under polynomial functions. All right. So there are lots of things happening. Now, we only talked about limits at infinity at this point. We did talk about a couple of transcendental functions like inverse tangent and sine of x over x. But now we want to focus our attention on the algebraic functions. So these are polynomial, rational, radical, and roots functions, and so on. All right. And so let's go to the second part of this video on section 4.6 to study those.